We can send probes to the edge of the solar system, but humanity has barely penetrated our own planet's skin. The deepest hole ever dug maxes out at just over 12 kilometers. To go any further means fighting an impossible war of physics. For every kilometer we travel downward, the rock becomes hotter, and the gravitational pressure becomes intense enough to crush steel into scrap metal. Since we can't physically drill down to take a look, how do we actually know what is down there? How do we know the Earth isn't simply solid rock all the way to the center? We find traces of this hidden world without ever digging a hole. Volcanic eruptions spew molten magma from depths we can't reach, and meteorites, built from the same primordial debris as the Earth, provide a chemical map of our planet's hidden makeup. But those surface remnants only reveal a fraction of the story. Because physical excavation is impossible, scientists rely on planetary-scale indirect evidence to X-ray the Earth's hidden depths. This planetary X-ray is powered by seismic waves. Every earthquake sends massive pulses of kinetic energy pinging directly through the Earth's interior. This cross-section shows P waves passing completely through the planet's interior, but S waves only move through solid material. Hitting liquid, they abruptly stop, creating a wave-free shadow zone. By tracking these waves, geologists map the exact boundaries inside the planet. These seismic shadow zones prove our planet is divided into radically different states of matter. Armed with this acoustic map, we can finally begin a virtual descent. We start our plunge on the outermost layer, the crust, also known as the lithosphere. The lithosphere is the rigid, rocky outer shell of the Earth. Compared to the mass and volume of the planet beneath it, this rocky skin is paper-thin, accounting for barely 1% of the Earth's total mass. This diagram illustrates the two types of crust. On the left is the continental crust, the landmass we live on. It is primarily made of silica and aluminum, giving it the shorthand name Sial. Sial stretches up to 60 kilometers deep under high mountains, but it is relatively low in density. The submerged block on the right is the oceanic crust, composed mainly of silica and magnesium, or SEMA. It is only 5 to 10 kilometers thick, but because of its heavy magnesium content, it is physically denser and heavier than the continental Sial floating beside it. Every mountain range, deep ocean trench, and chapter of human history exists exclusively on this eggshell-seam layer of Sial and SEMA. Drilling past the crust, we hit the Moho Discontinuity, or the Moho. Discovered by tracking seismic shifts, the Moho is the exact dividing line where the brittle, solid crust ends and the deeper layers begin. Crossing the Moho drops us directly into the Mantle. This layer accounts for a massive 84% of the Earth's volume, plunging 2,900 kilometers down, while temperatures surge toward 4,000 degrees Celsius. The upper section of this layer is called the Asthenosphere. The Asthenosphere is a partially molten, highly viscous region. Under intense heat and pressure, the rock here behaves like thick plastic, allowing it to slowly flow over time. Because this layer moves, the brittle crust resting on top of it moves too. The massive tectonic plates that make up our continents are actively sliding across this viscous, flowing asthenosphere. That means the solid ground beneath your feet is essentially an illusion. We are living adrift on a slow-moving ocean of superheated rock. Pushing deeper, roughly 2,800 kilometers down, we hit the Gutenberg Discontinuity. This is the exact depth where seismic S-waves suddenly vanish, proving we have breached a liquid barrier. We are now inside the outer core. It is a violently churning ocean of liquid metal, reaching temperatures of over 4,400 degrees Celsius. Pushing through that liquid chaos takes us into the dead center of the planet, the inner core. Here, temperature spikes to a staggering 6,000 degrees Celsius, matching the surface of the sun. The chemical makeup of the core is almost entirely composed of heavy metals, specifically a pure alloy of nickel and iron. Geologists refer to this dense metallic mixture as knifey. At 6,000 degrees, iron and nickel should instantly vaporize, yet the inner core remains completely solid. The crushing weight of the entire planet pushes inward, forcing the molten knifey to compress into a solid, impenetrable sphere. This ultra-dense, highly pressurized sphere of solid metal is the thermodynamic engine that powers the entire planet. If we reverse course and launch back up from that blinding white core, tearing upward through the mantle and bursting back onto the surface, we can finally see how that deep internal heat shapes the world around us. Radioactive decay inside the core continuously heats the mantle, causing molten rock to rise, cool, and sink in cyclical convection currents. These endogenous forces, internal geological pressures, drag against the crust's underside, fracturing the lithosphere and driving tectonic plates into one another. When those colossal plates crash together or pull apart under endogenous pressure, buckling to form towering fold mountains, fracturing to create block mountains, and rupturing to let magma escape. But as soon as that land is pushed upward, exogenous forces take over. These are external environmental factors, like the relentless wind, continuously flowing water, and the heavy, creeping glacial ice. These forces immediately begin grinding those fresh mountains down, carving deep valleys and depositing sediment to build flat plains. It is a continuous loop, driven by the Earth's distinct layers. The heavy iron-nickel core generates the heat, the flowing plastic mantle of the Asthenosphere acts as the conveyor belt, and the brittle, thin crust of Sial and Saima gets fractured and reshaped. Every static mountain peak and quiet valley we see today is merely the temporary outermost skin of a violent, continuously operating subterranean machine.
You know, we've mapped galaxies millions of light years away. We've put rovers on the surface of Mars, but one of the most incredible maps ever created is of a world we've never, ever seen. Today, we're taking a journey to the center of the Earth to see how we managed to chart the world right beneath our very feet. It's a really fair question, isn't it? We've literally left footprints on the moon, but we've barely managed to scratch the surface of our own planet. So why is that? Well, it's because the heat and the pressure, just a few thousand kilometers down, are way more extreme and hostile than the vacuum of deep space. Okay, so if we can't physically go there, how on earth do we have such a detailed map of what's inside? I mean, how could we possibly know about all the different layers, what they're made of, and whether they're solid or liquid? Well, the answer is pretty cool. Scientists have to be detectives. They can't visit the scene of the crime, so to speak, so they have to piece it all together by analyzing the fingerprints our planet leaves behind, clues that tell an amazing story about what's going on way down deep. And these are their three main detective tools. The first one, and this is the big one, is listening to the echoes from earthquakes. They also study the stuff that volcanoes spew up from the depths. And get this, they study meteorites that fall from space. They're like little cosmic fossils that tell us what the Earth was probably made of when it first formed. But the most powerful clue by far comes from seismic waves. You can think of them like a giant X-ray for the entire planet. P waves, or primary waves, are tough. They can power through just about anything. But S waves, the secondary ones, have a weakness. They absolutely cannot travel through liquid. The second they hit a liquid zone, they just stop, creating a shadow. And that shadow tells scientists exactly where solid ends and liquid begins. All right, so now that we know the detective work involved, let's take that journey ourselves. We're going to peel back the layers one by one, traveling from the ground we're standing on all the way down to the planet's fiery heart. You know, the simplest and best analogy for this is to just picture a hard-boiled egg. You've got the super thin, brittle shell on the outside, that's the crust. Then you have the thick, fleshy egg white, that's the mantle. And right in the middle, you have the dense yolk, that's the core. So let's crack it open. We start right here, on our home turf, the crust. It's everything we see, everything we build on, everything we know. But here's the crazy part. In the grand scheme of things, it's an impossibly thin and fragile skin. It's only about 1% of the Earth's entire mass. Relatively speaking, it's thinner than an eggshell. Now, this crust isn't all one piece. It's actually split into two very different types. You have the continents, which are made of thicker, lighter rock, and then you have the ocean floor, which is made of thinner, but much denser, heavier rock. This difference in density is absolutely key. It means the lighter continents are literally floating higher on the layers below them. Okay, as we continue our journey deeper, we hit our first major boundary. It's called the Moho Discontinuity, or just the Moho for short. Now, it's not a physical line you could see, but it's a zone where those seismic waves we talked about suddenly speed up, which tells us we've hit a totally different kind of rock. We've reached the floor of the crust. So once we're past the Moho, we are officially in the Mantle. And this place, this is the true engine room of our planet. It is absolutely enormous, a 2,900-kilometer thick layer that makes up a staggering 84% of our planet's total volume. Tucked away in the upper part of the Mantle is this really critical zone called the Asthenosphere. The best way to think about it is like a layer of incredibly thick, hot, gooey taffy. It's this weak, flowing layer that the solid tectonic plates are slowly drifting on top of. It's what drives everything from continental drift to earthquakes.
We keep going deeper, and we hit our next big boundary, the Gutenberg Discontinuity. And this is where things get really interesting. Remember those S-waves? Right here, at this depth, they completely vanish. They're gone. And that is the smoking gun, the undeniable proof that we've left the solid rock of the Mantle and have just hit a massive layer of liquid.
And that brings us finally to the very heart of our planet, the core. It's a giant sphere of super dense metal, mostly iron and nickel. And get this, it's almost the size of the entire planet Mars. But it's not just one big ball. It's actually divided into two very distinct parts.
And the temperature down here? It is almost impossible to wrap your head around. We're talking about 6,000 degrees Celsius.
Just to put that into perspective for you, the very center of our own planet is burning with the same incredible heat as the surface of the sun. It is a truly extreme, unimaginable environment. So this brings up a great little paradox. If the inner core is even hotter than the outer core, why is it solid while the outer core is liquid? It feels backwards, right? Well, the answer is one word: pressure. The weight of the entire planet is pressing down on the center, squeezing those atoms so incredibly tight that they literally can't melt. So we've done it. We've completed our journey from the shell to the yolk. We've mapped a world we can't see. But why does any of this really matter to us, living our lives all the way up here on the surface? Well, this layered structure is pretty much everything. It's what makes Earth a living, breathing, dynamic planet. That churning mantle is what's moving the continents and building mountains. That swirling liquid outer core, it's a giant dynamo, generating the magnetic field that protects all of us from the sun's deadly radiation. And then there's the crust, this fragile stage where life, as we know it, gets to play out. Every single layer is connected. So when you think about it, this map of our planet's interior is one of the greatest detective stories science has ever told. It's a crystal clear picture of a world we can never visit. And it really makes you wonder, if we've managed to learn all this without ever leaving the surface, what other profound secrets are still waiting down there, buried thousands of kilometers right beneath our feet?